Yeah, today we are going to continue talking about probability. And today we are going to talk about a special rule of probability that we call the addition rule. And there is a couple variations of it that we'll talk about. Before we talk about the rule, what we need to talk about is the idea that helps us decide which version of the addition rule we're going to use. And that is deciding whether two events are mutually exclusive, also known as disjoint, or if they are not. Mutually exclusive means that they can't happen at the same time. So, for example, when you are driving through an intersection that has a traffic light, the light being green and the light being red are mutually exclusive. You can't have a green light and a red light at the same time. Those are considered mutually exclusive events. They're considered disjoint events. So if I were to show this in a Venn diagram, which I think you probably have some experience with, mutually exclusive events are a Venn diagram with two circles that don't overlap. So here we have a red light and a green light. They're disjoint, they're mutually exclusive. So for example, if I had a bunch of people who all knew their blood type, and I randomly selected one person with type A blood, and I randomly selected somebody with type O blood, they could not be the same person because those two blood types are mutually exclusive. They are disjoint. Events that are not mutually exclusive, they are not disjoint. I should say not disjoint here. That's where we have the Venn diagram, and please pardon my poor drawing using my tablet, is where we have the circles that overlap. So if we randomly selected a student from this school that was female and randomly selecting a junior, there is some possibility of overlap there, the students who are female and juniors. And so it's possible that I select one student that fits both criteria. So that means being a female and being a junior are not mutually exclusive. They are not disjoint. And so we have an addition rule for finding probability for two or more mutually exclusive events, and then two or more not mutually exclusive events. And we can use Venn diagrams to help us out if we want to. I think visuals are good. You don't always need them, but I'm going to use them in the lesson as an example. So here is our rule for mutually exclusive events. These are events that are disjoint, where the Venn diagram is two circles or more that don't overlap. So here we have a circle to represent event A, whatever that is, and event B, and they don't overlap. So if we would like to know the probability of event A or event B happening, and this is this symbolic notation of that, the sort of U symbol. I believe in geometry, you might have used the upside down V. The probability of event A or B happening, if they are mutually exclusive, we can just take the probability of A and add to it, hence the addition rule, the probability of event B. We can just add those two probabilities together to find the probability of one or the other happening. So here we have some different animals. You can pause and read this if you'd like. We have mammals, we have birds, and we have fish. And I'm just going to draw a quick Venn diagram. You don't have to, again, but I think they're helpful. It's not pretty, but it helps. I have birds, I have mammals, and I have fish. 75 birds, 59 mammals, and 68 fish. And they are mutually exclusive because you cannot be one and the other one at the same time. So there's no overlap here. And so we have a total of 202 animals. And what we want to know is the probability, if we randomly select one of these 202, what is the probability it is either a mammal or a fish? And or in probability means to add. So I want to know the probability of it being a mammal or a fish. And you can use or you can use the U symbol, whichever one you are more comfortable with. I'm not going to be picky about that. But you should get used to using this probability notation. Because they're mutually exclusive, we can just add the probability of being a mammal to the probability of being a fish. So we have 59 mammals out of 202. So the probability we randomly select a mammal is 59 over 202. The probability of randomly selecting a fish is 68 over 202. And so if we add these two fractions together and we divide, we get a decimal. And I'm going to round that to 4 decimal places. That's sort of my rule. You don't have to, but we want to at least have a couple decimal places. 4 is usually pretty good because if we convert this to a percentage, it gives us 2 decimals after the or 2 numbers after the decimal for a percentage. Remember, probability is always some number between 0 and 1. So this is a probability and this is a percent chance. Just some semantics, some language things to pay attention to. And so the probability that we randomly select out of these 202 animals, a mammal or a fish, is 0.6287. There's a 62.87% chance that we select one or the other of those. We have another example here of these different employers and the number of employees they have. And I'm just going to use one letter for each. So I have U for US Steel, A for, I believe that's Alcoa, B for Bayer Material. And again, they're mutually exclusive here. I suppose you could work at more than one of the companies, but in this instance, let's say we can't. And so if we want to know the probability of randomly selecting one of these 1,110 employees total, that one of them is from US Steel or Alcoa, and that should be an L there. Because they're mutually exclusive, we can just add the probability of working at US Steel and the probability of working at Alcoa. So we have 110 out of 1,110. And we have 750 out of 1,110. We add these together. You can use your calculator to help you. You really only need to add the numerators and get 860. Divide that by 1,110 to get 0.7748. And again, I like to do 4 decimal places. So the probability of randomly selecting a person out of these 1,110 people that works at either of these two companies is 0.7748. So there's a 77.48% chance. When we get into these non-mutually exclusive events, so 2 events that have some overlap, there is a place there where you can be in event A and event B at the same time. This represents sort of like an and. We have or and probabilities. We'll talk more about and probabilities next time, but the place where these two overlap is an and probability. It means they are both at the same time. So if we want to calculate the probability of event A or event B, so that's still or, this symbol over here means and. You can turn that into a letter A. That's how I remember it. We still add the probability of event A and event B together, but because there's some overlap, we're sort of counting something twice. We're counting some of the elements in the event twice because they're in both A and B. So we have to subtract out that overlap, this piece right here, so that we don't count it 2 times. So this sort of add-on to the addition rule if we have the overlap, if we have 2 events that are not or non-mutually exclusive. So we have a deck of cards. Apologies to those of you who aren't familiar with the cards, but I have some you can borrow if you want to take a look at them. We want to know the probability if we draw 1 card, it's either a 9 or a diamond. Well, we can have some overlap, which is a 9 of diamonds. That's my best diamond. So the probability of a 9 or a diamond, we take the probability of getting a 9, add to that the probability of getting a diamond. And then we have to subtract out of that the thing we're counting twice. So we're counting the 9 of diamonds in this probability, and we're also counting it in this probability. So we got to subtract it out 1 time. So it's only being counted once. So we have 4 9s out of 52 cards, and we have 13 diamonds out of 52 cards. Whoops. And one of those things is a 9 of diamonds. That's the overlap that we've counted twice. So we're going to subtract that 1 out. We can do 4 plus 13 minus 1 and then divide it by 52 to get 0.3077. So again, we have to subtract out 1 out of 52 because we counted the 9 of diamonds in this probability as well as this probability because it's one of the diamonds and it's one of the 9s. So we take that overlap out to find our final probability. Similar in this scenario, and again, like I said earlier, I'll probably talk through this a little too fast for you to read it while you listen, so go ahead and pause if you need to read through this first, or listen and then pause and read it back. We have some male and female hospital workers that are, some of them are nurses, some of them are physicians. We want to know the probability if we were randomly select one of these people. What is the probability that that person would be a nurse or a male? And there is some overlap there because I have some nurses that are also males. And so we can add these 2 probabilities and then subtract away the overlap. So the nurses that are also males. In this hospital unit, there's a total of 13 people. 8 of them are nurses, so my probability is 8 over 13. My males, there are 3 males. Since we have 7 nurses and 3 physicians that are female, that leaves 3 left over that are males out of all 13. Since we have 7 of the 8 nurses are female, that means 1 of the nurses is a male. And so that is our overlap. We counted that male nurse twice. We counted them in the nurse probability and the male probability. So we just got to subtract one of those away to get a final probability of 0.7692. Before you move on to the practice, if you had any questions on any of these problems, any of the problems you'd like some clarification on, please ask that before you go and try and do some on your own. I recommend that you do the practice on paper first and then have me check your work so we can have a discussion about maybe any mistakes that may have occurred. If you've got your questions answered, please do the practice. Take your time on these, and good luck.